Alright, so welcome back everyone. So I'm finally back after a hiatus. So in this video, we are going to solve this coding question, which is linked list cycle. Okay, so it is a very famous question. It is asked in various companies like Amazon, Snapdeal, and many more. So the question is pretty straightforward. We'll be given a linked list. So when I say we'll be given a linked list, we'll be given a head pointer. And we have to detect a cycle in the linked list if it is present or not. Now you know what is a cycle, right? So if a node points to some of its preceding node, then we can say there is a cycle present in the linked list. Now there's some explanation given here in lead code that's maybe confusing for you, but you just need to, by looking at the function definition, you can be very sure that you'll be given a head pointer and you just have to return a bool which is true if the cycle is present or false if the cycle is not present. Now I will request you to think about how we'll approach this question, and I'll roll the intro. Alright, so the way I'm going to show you the solution is, now one thing I could do is I could just simply show the optimized solution, but I'm not going to do that. So what I'll do is I'll simply walk you through how a normal person approaches a problem. So first we'll discuss the brute force solution, and then we'll actually discuss the optimist solution, and of course we'll discuss the time complexity. And I'm going to show you the solution in C++. You can definitely implement them in your favorite programming language, Java or Python, I guess, for most of them, or maybe JavaScript. So why wait? Let's start. All right, so here's the linked list I have taken. I have created my linked list. So it contains five elements, and there is a cycle present at this node, or starting at this node. Now the first approach uses a hash table. Now why hash table? Uh, I'll come to this in a point. So the first approach uses this hash table approach. Now what we are going to do is, we are going to every node, and first we are going to check if it is present in the hash table. If it is present in the hash table, then we have the cycle. If it is not present in the hash table, then we are going to insert it. Okay, so let me repeat myself again. So we are going to maintain a hash table. So basically we are using some extra space here. Okay, we are going to use some extra space here. There's no doubt about it. Okay, and we are going to go through each and every node from the beginning. And if that node is not present in the hash table, for example, this 3, if it is not present in the hash table, then I'll include it. Now, when I say I include this node, I basically include the pointer. Now, why the pointer, not just the value? Because let's be honest, because what if the linked list will be something like this? It will be some 3 to 3 and null. Now, if something like this has happened, if I include some value 3, then value 2, and then this 3 and 3 will be same, which they are not, right? So you're getting what I'm trying to say. If you insert this 3, insert this 2, and whenever you again try to insert this 3, according to the way hash table works, it will seem like these two values are same, right? So we don't want that actually. We actually want to we include the pointers, not the values. You'll understand it. Don't worry. It's very simple. So first, let me just do a dry run of the algorithm. So first, we'll check if 3 is present. 3 is pointer, if you will, is present in hash table. Not. I'll include it. I'll go to this 2. Is 2 present in hash table? No. I'll include it. Then I'll go to this -1. Is -1 present in hash table? No. So I'll include it. Is 3 present in hash table? Now it's important. This 3 node is different. If you are confused, see it like this way. Its address may be 100 and consider its address may be 500, something like this. Okay, so these two are different, right? These two are not same node. So we don't want them to look same, because if this link was not present and when try to insert this 3, it would our algorithm would feel like, okay, there is a cycle, but that's not right. That's not. So what we're actually trying to do here is, uh, we are starting to traverse the linked list in a way, in hope if there is a cycle, I'll eventually reach to a repeating node. Okay, so what I'm saying is, when we try to insert these nodes, I'll keep on inserting them in the hash table in a hope that I might reach this 2 again, right? This is the first node. of the loop, if you will. If you just think about it, this is the first node of the loop. So we keep on inserting the elements in a hope that I'll come to this 2 one after a while, and I'll be able to know that, okay, so 2 is present in the hash table. So there is definitely a cycle. So that's the idea. Okay, so where was I? So we lastly insert -1. We are now at this 3. This 3 is different. This 3 is not present here. Okay, so I'll include it. Why? Because we're including the pointer. Okay, then I'll come to the 0. The 0 is not present here, so I'll include it. Now the 0 is next. This is interesting. Uh, this is the starting point of the loop, right? This is the starting point of the loop. So that's the idea of this algorithm. We start including the nodes and hoping if there is a cycle, I'll eventually come back to the starting point, right? That's very obvious to see. Now when I try to insert this 2, now there is a match. Okay, now we'll find, okay, so 2 is already present. And if such a thing is found, if I try to insert an element, if a value is found, I'll simply return true, right? So if 2 is found, then I'll simply return true. Otherwise, if cycle will be not be present, eventually we'll reach the end of the list. One classic example would be something like this. If it's 3, 2, 1, something like this, and this is null, I'll first include 3, then I'll include 2, then include 1, and then I'll eventually go to the end of the list. So in this case, there will be no cycles, right? So if we reach the end of the list, it's good. We'll return false anyway. But if there is a cycle, we will be definitely reaching the starting point of the loop after some time. After some time means after traversing the entire list, we'll definitely reach the starting point of the loop, right? Now, I hope you understand it. The time complexity of this approach is pretty simple. If we just see what we are doing is we are going through each and every element of the list, and eventually when we reach the tail, this is tail, right? Eventually when we reach the tail, we are going to bump to the first, that is a bump to the entry of the loop, and the algorithm will break. Now if you see, it's clearly the time complexity is clearly big of n, and we're n being the size of the linked list, because we're going to traverse each and every node and just one more computation, so n plus 1, but it doesn't matter, big of n. And space complexity, we are using this hash table, right? So that's why the space complexity is also big of n, because at the very max it might happen that, because at the very max we have to actually, not at the very max, we have to actually store each and every node if we want to read the starting node of the node, right? I guess you know why it makes sense, right? Because we have to include each and every node, then and only then we'll be able to know, okay, so the starting point of the loop has came. Now, come to the reason why I use hash table is because if you see at every iteration, what you are doing, we are inserting that node into the hash table if it is not present. So we are going to actually insert those n nodes. Now, the hash table is the only data structure which provides that constant insertion. There's no other data structure for that. So yeah, that's the very simple reason why we use hash table. Alright, so here's the C++ solution, very straightforward. So here's my unordered map. I have declared it, and its keys of type the node, and the value, I really don't need this value, but just for the sake of it, I'm taking it. It really doesn't affect that complexity. Okay, the code will execute perfectly fine. There is no doubt about it. Then what we are going is we are going through each and every node. So while head not equals to null, so if list will be empty, eventually this loop will break out and we can return false. Okay, so if list will be null terminated, that it won't contain cycle, or it may be empty, or that's the edge case, right? So if edge cases are also handled. If list is empty, then we simply break out of it. Or if it ends, then eventually this loop will break and we can return false. Okay, the list doesn't contain cycle. If otherwise, what you have to do, we just have to check at every point. Okay, if this head is present in this hash table, this nodes.c, so I'm just using this count method. Okay, and by the way, if you remember, this unordered map in C++ contains unique keys, so you cannot insert an element more than once. So if it will be present, this count will be 1. Okay, so that's that. That's just language level details. That's not required for this video. So again, let me repeat the solution. We created our hash table here, which is unordered map here in this case. I'll go through each and every node. Then first I'll check, okay, if this node is present in the hash table. Okay, if it is present, then simply return 2, because we have bumped to the starting point of the loop, right? So what I'm saying is, we inserted 3, 2, -1, 3, 0, and again I come back to this 2. So if its address was 200, it was already stored, right? So if I bump back to this again, So if this condition is met, it means I bump to the starting point of the loop. So simply return the true. Otherwise, simply store this node and move ahead. Right. All right. So it's time to discuss the optimist approach to this problem. As we already know, the interviewer will not be happy with the extra space that we are using. And one more thing, the annotation that I did in case of this approach or brute force approach will be available in the description box, so you can check it. Now, yeah, coming to the Optimus solution, there is a famous name. It's a famous algorithm for this solution. It is called Floyd's hare and tortoise algorithm. Now, why it's called hare and tortoise algorithm, you'll know in a bit. But it's a beautiful algorithm. Now, before I discuss the approach, I would like to tell you that it's completely okay if you're not able to think the optimized approach on your own. It happens. I'm also an average guy. I have also watched the solution, and that's why I know this. Okay, I am no geek, and there are people who might guess the solution, who might get the optimized solution in just super fast way. But for average guy, it might not happen. You don't need to worry about it. That's what the solutions are, right? How can you expect to just know each and every optimized solution in a bit? This guy is behind them. Floyd has worked so hard to come up with this algorithm. Now, how can you even think that you can come up with that approach in just a day or two? It will take time, right? And sometimes it's not worth. That time is not worth. It's better just watch the solution and move on. So, enough pep talk. Let's come back to the algorithm. So the algorithm is very simple and straightforward. The way algorithm works is we cannot use extra space here, right? So it works by creating two pointers. I'll use very analogical name so that things get clearer to you. The first name will be tortoise, and next name will be hare. Some you will see the slow and fast as names. Okay, this tortoise will might be called slow, and this hare will might be called fast. But I thought, why not just use the images that makes more engaging, right? So yeah, that's what I thought. So the idea is pretty simple. What we do is we move this tortoise uh, by one every iteration, and we move this hare as it is a hare, double the speed of the tortoise. So we move it two times at every iteration. Now, if you think intuitively, what will happen is if this moves slowly, one step at a time, like this, now eventually this hair will catch up, right? Eventually this hair will catch up to this. So what I'm saying is just think intuitively, right? This turtle moves, this tortoise moves slowly, one step at a time, one step at a time, one step at a time. Eventually this hair will catch up, right? Because it is moving so fast. Even if it doesn't make sense, it will make sense. Just think about it. It's very easy. So yeah, algorithm like this way, what will happen is we'll start moving the tortoise by one and hare by two. Initially, both will be pointing the head. Okay. Then what we do is we start moving at every iteration. We move the tortoise by one and hare by two. So hare will be here. Okay. This was the first iteration. Then at second iteration, I'll move again the tortoise by one and this hare by two. So hare will be here. Now at another iteration, this tortoise will be here. So these are pointers. Okay. And this hare will be one, two. It will be here, right? Now at next iteration, tortoise will be here, and now the hare will catch up. Now at this moment, in this they were equal. So basically, in terminology, if fast equals to slow, so these are just pointers, right? If they both are equal, then means there is a definitely cycle. Why is that? Because the tortoise was moving slowly and the hare was moving at the double the speed. So what happened is, uh, tortoise was moving slowly, right? So tortoise go here, 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 and hare was so fast that it actually completed the cycle and meet him back. Make sense? I think it makes sense. That it is a very simple solution. Now let me tell you why exactly this works. Okay, intuitively it might be clear. There's no doubt about it. And let's think a bit more why this works. So let's just say there is our here is our tortoise and here is our hare. Okay, hare is just one step behind it. So let's just assume that tortoise came from a long journey and it is right now here, and this hare just completed the cycle and now it's one step behind. Now the next iteration, this turtle will move here. or tortoise will move here, and this hare will simply reach here, right? So if it's just one step behind, if what I'm saying is if hare is one step behind, if it is one step behind, it will catch up. It will catch up with the tortoise in one iteration. Okay. So why is the guarantee that hare will catch up the tortoise? So if one iteration, it is very straightforward. Now what if there were two iterations? So let's see what happens if it is two step behind. Okay. So this is our hare, and let's just say the tortoise is currently here, and there are some nodes here. Okay. So you can consider it if cycle will be present, it will be present somewhere here, or maybe something like this. Okay. I'm just talking about any two nodes. Tortoise is two step ahead the hare. At next iteration, it will move here, and hare will move here. Then if you observe it, we are actually now in the first case. If we have the first case, it is the hare is one step behind the tortoise. Now in next iteration, it will definitely catch up, right? Hare will definitely catch up. So you can just see how the pattern is developing. If the hare is three steps behind, it will catch up the turtle in three iterations, right? So if it was one step behind, it would have catch up in one iteration. If it's k steps behind, it would catch up in k iteration. Now, so that's a guarantee that definitely if there is a cycle, this hare will catch up with the tortoise. Now you might say, why did I discuss it? Because we need it in this finding out the time complexity of this approach. Now space complexity, first of all, let's discuss it. Space complexity, we are not using any extra space. We are just using two pointers, this fast and slow. So that's no space complexity. So yeah. So let's talk about the time complexity then. What will happen if you just think intuitively? Also, we will will nearly do n iterations. Okay, n being the number of nodes, and let's think a bit more. Okay, intuitively it makes sense that we will only cover n nodes, but why does it happen? Okay, why it is like that? We'll only cover n nodes at max. Let's see. All right, so let's see. Let's say these are some starting nodes. Okay, so there are some nodes here, and let's say the tortoise has reached the starting point of the loop. Okay, let's just say the loop starts from here. The loop starts from here. There are some nodes here, and there's something like this. Okay, there are many nodes. It doesn't matter. Now, the very worst thing what can happen. Okay, at the very worst, what might happen is uh, the hare might be the entire cycle behind the entire cycle behind. If the length is, you can consider this length L. Length L meaning just number of links or number of nodes within the cycle. Okay, but the very worst, what can happen is the hare might be L steps behind this tortoise, right? L steps or maybe K steps, whatever. Let's just call the cycle length L. Okay, so this is the cycle length. Okay, if this is ambiguous to you, just consider this. Okay, so here the cycle length is 1, 2, 3, 4, or maybe you can count in terms of this edge length 1, 2, 3, 4. Okay, so that's what I'm talking about. So at the very worst, it might happen that tortoise is here and hare is here. Okay, depending on how nodes are arranged, at the very worst, this can only happen, right? It is maximum, at the very max, this hare might be L steps behind the tortoise, right? And we have already discussed it. If it is K steps behind, it will take K iterations for this hare to catch up with this turtle. So let me take a different color. We have already done here, let's just say this number is M. These are some starting nodes, whatever you want to name them. We have done this M iterations, and then we have to done this L number of iterations, right? So how many total iterations we have to do? Let me write it here. We have done this non-loop nodes, if you want to name it that way, and then we have to actually move to the entire cycle, right? So you can just think of it in terms of the turtle node. How many distance the turtle node travel? Because we know that every iteration we move both the nodes. So we can just to think of time complexity, we can just think, okay, just let's think of in terms of turtle, because we know that if they both equal, we'll just stop it, right? So let us think in terms of a turtle only. So let us say turtle travel these m nodes, and it takes here L iterations for this hare to reach this turtle. So if you just think about this, there will be m nodes and there will be L nodes. L nodes traverse. So this m plus L what is the total number of nodes, right? These are what? These are total number of nodes only. Very simple. So that's why the time complexity is also big of n, because we are not going to travel, we are nearly going to travel n nodes only, uh, approximately. So at asymptotically, you can think of it like the time is also big of n only. We are not going to travel asymptotically more than n nodes, n being the total number of nodes. Alright, so here's the solution. I've created my both pointers. You can name it fast or slow. Okay, I just named it because I wanted to make this thing clear. And initially, they both point to the first node. That I already told you. They both start from the first. Now, here's the condition that I've written. Now, some people also break these conditions, but I found that it will be more clear this way. Now, what is this first condition? This tortoise will be equal to null only if the list is empty, right? If the list is empty, this will be null because this head will be null. So we can simply return false. Okay, if list is empty, then how can there be a cycle? So that's what this condition does. If the list is empty, this case is handled here. Otherwise, we simply go and increment tortoise by 1 and hare by 2. Alright, and if a match is found, we simply return true. And at every iteration, we need to check two more things. Since we are moving the hair by 2 steps, we need to make sure, okay, first if hair exists and then hair of next exists. Because if you see, we're accessing hairs next of next. So first we need to make sure that this thing works correctly at every iteration. First need to make sure if hair exists. Okay, when if hair exists, does hair of next exist? That's what we are doing here. And this will also take care of the case when the list will be null terminated, so it won't contain any cycle. So this handles edge case when the list is empty, and this handles the null termination part. You can trace it the solution, it's very simple. And of course, after incrementing tortoise and hare, if they become equal at every iteration, we can simply return true. Okay. So yeah, that was that. That was the optimized solution. Okay. I really hope you got something out of this video. If you do, please give a like and thank you.